Hello and welcome back to Algebra, the video series where we talk a lot about algebraic structures like groups, rings and fields. And in today's part 19, we will finally tackle an important result in group theory known as Lagrange's theorem. Indeed, this one will connect the results we have discussed in the last videos. However, before we formulate this nice theorem, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the Steady membership you can download a lot of additional material like quizzes, PDF versions and books. Now for the start of this video, let's quickly recall what we already know from the last videos. The assumptions we have are always the same. We fix a group G and a subgroup U in it. So for example, we could say that this set represents G and then we find a subset U in it. This subset can be small or really large, but it definitely contains the identity element of G. And now we can just form copies of this subset and we call them the right cosets. And the common notation we have for such sets are just UG because the elements are formed in this way. In fact, we would speak of the left cosets if we put G to the left of U here. Indeed, this is the only difference and therefore we will just focus on the right cosets here. And now if we form a union over all right cosets, we get our original group G back. In fact, this union is actually disjoint if we ignore the elements where the right cosets coincide anyway. Or to write it more formally, two right cosets are not disjoint if and only if they are already the same set anyway. Hence, the best way to rewrite this union as a disjoint union would be to actually count the number of cosets we have. In other words, this one is just about the cardinality of a set of subsets. So we just consider the collection of all possible right cosets of U. Of course, if we deal with a finite group, this is definitely also a finite set. And then we just want the number of elements in this set, in other words, the cardinality. Hence, if we know this cardinality, we can write G as a disjoint union of right cosets. In order to make it simpler, let's say we have a set capital I that has the same cardinality as this set. So it's an arbitrary index set which we can just use to put an index to the elements of G. And we don't need all the elements of G, we just need these ones that describe all the right cosets. And this implies that we can write G as a disjoint union now. So each coset just appears once in this whole union. So please remember here, we choose the elements in such a way that we get a disjoint union. And just to be clear, this means that any intersection we have here between two sets is just the empty set. So for two distinct indices, we get two different sets. Okay, and now since we have this nice decomposition for any group G, this cardinality here gets a special name. This is an important definition and I can already tell you it's called the index. So any subgroup U has an index in the surrounding group G. So for the definition as before, we just take all the right cosets and count them. And then we simply call this cardinality the index of U in G. And indeed, it does not matter if we consider the right cosets here or the left cosets. The number that comes out is exactly the same, but for the definition, let's choose the right cosets. And indeed, in group theory, this index gets a special name. We write G:U. And since we talk about a cardinality here, we also use the vertical lines around it. So you see, we either have an infinite cardinality here or just a natural number. And maybe to make the whole thing clearer, let's look at some trivial examples first. Indeed, the simplest case would be to consider G as a subgroup itself. So the question is, what is the index of G in G? Obviously there we only have one right coset, which means that the index is equal to 1. So also in the case that G is of infinite order, this index stays a finite number, namely 1. And on the other hand, the second trivial case would be just the neutral element as a subgroup. Obviously there we have a lot of right cosets, namely for each element in G. Therefore the cardinality here is exactly the cardinality of G itself. So you could say that these are the two extreme examples and all other subgroups have indices in between. So maybe let's go to a more concrete example, namely the integers with the addition. And there we already know that 2z is definitely a subgroup. However, since we have the addition as the group operation here, the notation for our right cosets should be different. So for example, the right coset with respect to the neutral element would be written as u plus 0. And this just gives us our subgroup u, which means the even integers. And on the other hand, we can also look at the right coset written as u plus 1. This shifts everything by 1, so we get the odd integers. Therefore, in combination, we already have the whole group G here. And this already tells us that we have all the right cosets and the index of our subgroup U is equal to 2. So this was quite simple, and maybe you can even see the generalization here. If you take another subgroup of Z, you can also easily calculate the index. So what I mean here is the index of mz in Z. In fact, you can just write down all the right cosets and you see you have exactly m of them. So our index here is given by m. So maybe that's good enough for examples now, and I would say let's immediately go to Lagrange's theorem. This one will now make the connection between the size of the subgroup and the index we have defined above. Therefore, our assumption here is still the same. We have a surrounding group and a subgroup in it. And now the size of G as a cardinality can be calculated with this index. Namely, take the size of the subgroup U and multiply it with the index. And that's it. This is the whole theorem of Lagrange. It gives you a calculation rule for cardinalities. It holds in general, but of course especially for finite groups this one is interesting. Moreover, in that case, the formula also tells us that we only need to know that two of the quantities here are finite. Because then we can also conclude that the third one has to be finite and we can calculate with natural numbers here. And this also implies that this nice index here can be written as a fraction, like this nice colon already suggests. Indeed, this is how you can easily remember Lagrange's theorem. And moreover, we can immediately look at a special case where we generate a subgroup U just by one element in G. And you already know the notation for that. We have a lowercase g in pointed brackets. And now if we are in the finite case, we know that the cardinality of G is also called the order of G. Hence, the formula tells us that the order of the group G divided by the order of the element G is a natural number. And this is a general result that definitely holds for any element in our group. And now you can already remember the order of a group element has to be a divisor of the order of the group. This is definitely something we already discovered in example, but now we have the general justification as Lagrange's theorem. Therefore, the only thing that remains now is to prove it. However, it turns out that we actually already have done it. Namely, we already have written G as a disjoint union of the right cosets. Moreover, we have chosen this index set I such that the cardinality is the same as the index. And moreover, we also know that the cardinality of all the right cosets is the same as the cardinality of U. Hence, we also get this equality for all the indices in I. Therefore, what we have here is just a counting argument in set theory. We know how many sets we have, and we know the size of each set, and then we just form the union. And since all the elements are different in the union, we just have a multiplication. So the number of elements in G is given as the number of elements in I times the number of elements in U. This definitely works in the finite case, but it's also correct for higher cardinalities. Indeed, it's really not so complicated because it's just a bijection argument with sets. And there we have it, Lagrange's theorem is proven. It's a really important result in group theory, and I can tell you what we can do with that with the next videos. So I really hope I meet you there again, and have a nice day. Bye bye.